Hello, welcome to lecture number 37 of the course Quantum Mechanics and Molecular Spectroscopy. As I told you in the previous lecture that we are going to look at some solved problems. So, today I am going to talk about the problems related to rotational spectroscopy. Okay. So, when you record a rotational spectrum, you get numbers B, things like that. How do you interpret the spectrum and what you have to do to get the spectroscopy correct. One of the things that you do in the rotational spectroscopy, record the rotational spectra of isotopomers. What do I mean? Okay. Now, if I have molecule HCl, okay. Now, there are various isotopes that I can think of. So, if I have HCl molecule, then I can have 1 hydrogen 35 HCl, or I could have 1 hydrogen 37 Cl. So, 37 and 35 two are isotopes of the chlorine atom, or one could have 2 hydrogen and 35 Cl. So, by the way, this is also called D. Okay. Deuterium is nothing but the isotope of hydrogen with 2 molecular atomic mass, or you could have 2 hydrogen 37 Cl. Okay. One could look at various isotopes, and you see when you look at the rotational constant B, or let us call it as B0, because at the equilibrium distance, this is given by h by 8 pi square I, where I is the rotational constant, I is the moment of inertia, sorry, moment of, and B naught is the rotational constants. Now, how do you get P naught can be measured by experiment. So, when you record the rotational spectrum, we know that the separation between the lines, so this is 2B, 4B, 6B, this is 0 to 1, 1 to 2, J values, J is equal to 0 to J is equal to 1, J is equal to 1, J is equal to 2 to 3, 3 to 4, etc. 8B, and the separation between them is 2B. Okay, this is pure rotational spectrum. Okay. Now, when you have rotational constant B naught, so that you can 2B or 2B naught can be directly measured from the experiment. Okay. So, this is experiment. Okay. But generally, so this is B naught, if you look at this thing, it will come out to be in hertz or second inverse or hertz. The in this case B naught is given, the unit of B naught is second inverse or hertz. Okay. But generally B naught is not measured in also measured in centimeter inverse. So, B naught is also measured in centimeter inverse. When I do, so you can do a quick conversion. So, if I measure B naught in centimeter inverse, then my B naught will now be equal to h by 8 pi square C I, where C is speed of light. And what is I? Moment of inertia. And I is given by mu r naught square. So, where mu is the reduced mass, R naught is the equilibrium distance. Okay. So, this is the necessary. So, in experiment it turns out, after doing the experiment, in one experiment what they have found, that 1H 35 Cl, the value of B naught was equal to 10.44 centimeter inverse, and similarly value of 2H Cl 35, the value of B naught is equal to 5.39 centimeter inverse. So, you see, when I substitute the hydrogen with deuterium, there is a drastic change in the value of the B naught. Okay. This is what I call as isotope effect. Now, let us use this and try to evaluate what is the length or the equilibrium length of the HCl molecule or DCl molecule. Now, we know that B naught in centimeter inverse is given by H by 8 pi square C I, which is also given by H by 8 pi square C mu R naught square. So, I can slightly rewrite this equation in R naught square is equal to H by 8 pi square C mu B naught. So, I am going to use this formula and plug it in and see what I will get. Now, H is nothing but 6.626 into 10 power minus 34 joule second. You can see this, you can verify if the formula is dimensionally correct. Okay. Now, 6.626 in 10 power minus 34 is the value of H, that will be in joule second, is not it? So, it is an action constant, joule second, 8 pi square, C is 2.997. Since I am looking at this centimeter inverse, I am looking at speed of light in centimeters per second. So, that will be 2 into 10 power 10 centimeters per second into mu. Okay, mu I need the reduced mass. So, if I look at 1H 35 Cl, then my reduced mass will be nothing but 35 by 36 into 1.66 into 10 power minus 27 kilograms. So, that will be nothing but 35 divided by 36 into 1.66 into 10 power minus 27 into value of B naught, which is 10.44. Okay. So, I can do little bit of equations and change do algebra. So, this 34 and this 27 will cancel, and then you will get 10 power minus 7, and this 10 power 10, and that will, this I can cancel and write 10 power 17. Okay. So, what I will get is that 6.626 divided by 3991.031 into 10 power minus 17. So, that is going to be the value. Just you can do the math, I have already done it. So, this will be now be equal to 1.660 into 10 power minus 20. So, R naught square. So, I take a square root, R naught will be now equal to 1.288 into 10 power minus 10 meters. You know 1.10 to 10 power minus 10 meters is nothing but your angstrom. So, this in R naught will be nothing but 1.288 angstrom. Similarly, for if I take the same value R naught square is equal to 6.626 into 10 power minus 34 divided by 8 pi square into 2.997 into 10 power 10. Now, instead of I take 2H35Cl. So, deuterium isotope DCl. So, that will be nothing but into 70 divided by 37, because 2 into 35 is 70, 2 plus 35 is 37 into 1.66 in 10 power minus 27 into, now the value of the rotational constant is 5.39 centimeter inverse. If I do the math, what I will get is R naught will be equal to 1.286 angstroms. Okay. So, what I get is the following: for 1HCl35, that is HCl with 35 isotope, for R naught will be equal to 1.288 angstrom, and 2HCl35, that is DCl, R naught is equal to 1.286 angstrom. Okay. So, minute changes in the isotopes do affect the lengths. Okay. Here the change is in third decimal. Okay. So, you should have that kind of calibration that will allow you to differentiate the bond lengths at third decimal. Okay. And mind you that the rotational spectroscopy is the only spectroscopic technique by which one can measure bond lengths. Okay. Now, this is just an example. So, let me just tell you quickly, okay, how we can use this problem to look at something else. Okay. Now, the other problem that one can look at in the rotational spectroscopy is, let us suppose a carbon monoxide molecule CO. Now, CO can have various isotopes. One of the isotope is, the standard one is 12CO16. Okay. The other one will be 13CO16. The third one will be 12CO18. Of course, the fourth one will be 13CO18. There is also oxygen 17, but we will not get into that, but these are the four possible isotopes that one can isotopomers. So, these are isotopomers of CO. Now, I do not have data for this, so I will going to ignore. Okay. So, for 12CO16 and 13CO16 and for 12CO18, the B naught in hertz is given by 57898.4 megahertz, and this is 55346.3 megahertz, and this is 55135.3 megahertz. Now, I can always convert megahertz or hertz into centimeter inverse. So, if I convert this, this will convert to be 1.9318 centimeter inverse, and this will be nothing but 1.8467 centimeter minus 1, and this will be nothing but 1.8396 centimeter inverse. Now, if you look at the difference, this is less than 0.09 centimeter inverse, and this is less than 0.01 centimeter inverse. Now if I have to distinguish between this and this, then my resolution of my spectrometer should be better than 0.01 centimeter inverse, or at least half of them, or this should be 0.09 centimeter inverse. So if I have to distinguish the isotopomers of my carbon monoxide, the microwave spectrometer, the spectrometer that records this rotational spectra, okay, should have very high resolution. So that I can separate out these isotopomers. By the way, oxygen 8 is not available, but carbon 13 is 1% natural abundance. Okay. In fact, there are spectrometers in which you can record the spectrum of this using natural abundance. Okay. Now, when I use this data and convert, okay, so I can use this data to convert. I know the values of B naught, so these are B naught in centimeters. So, by the way, when you got in centimeter, it is also called B naught bar. Okay. So, I have this in megahertz and also in centimeter inverse. I can use the value B naught is equal to H by 8 pi square I. This is nothing but H by 8 pi square mu R square or naught square, or B naught bar, that is in centimeter inverse, is H by 8 pi square C I, or H 8 pi square C mu or naught square. I can use one of them and plug in the values of mu. Of course, when you have these, the values of mu will keep changing. Then it turns out when you calculate all this, you will get R naught for 12C 16O is equal to 1.1285 angstroms, and you will get R naught for 13C O16 is equal to 1.2735 angstroms, and R naught for 12C 18O will be 1.27 1.128 5 angstrom. I might have done some mistake here, you can recheck. So, this is how one can use the rotational spectroscopy data to calculate the bond lengths. Okay. And one also has to calculate bond lengths of several isotopomers to get the statistically correct answer. Okay. We will stop it here. Thank you very much.